Okay, so in section 13.4, really they wanted you to look at two particular types of functions and think about what happens. So we're going to look at rational functions, and we're going to look at exponential growth or decay functions. So what if those functions were the rules for generating a sequence? Okay, so I don't know if you guys used this word last year. But a rational function, the key word then is ratio. So a rational function is a ratio of polynomials. And we can generalize these. And what we're going to look at is we're going to look at their end behavior. So what happens? So really we're starting very concretely. We're imagining we're using either of those two rules and we're generating a sequence of terms. And we're generating, and they're going to go forever. But we're really looking when we get towards the end, as we're towards this, is there some behavior that's happening? Is there something that we can sort of describe? Okay, so let's look at the first example. Okay, so here is the explicit rule for generating the terms, and that is a rational function. So a polynomial is when you have a variable, a single variable, and you're just multiplying it and powering it, add it together. Okay, so what I want you to do is I want you to put this into y1, and remember to use parentheses. Okay, so put this into y1, and then I want you to find a couple numbers for me. So I want you to go find y1 of, put in 100, and y1 and put in 1,000. And I want you to take a pause the video, go put this into y1. You'll need the x's instead of n's. You for sure need parentheses in the denominator, okay? And then come back to me, and then we'll talk about what you got, okay? All right, see you in a minute. Okay, you back? Okay, so we did y1 of 100. You should have gotten, it's like 0.51005. And when you do y1 of 1,000, you should have gotten like 0.501, and then I got a whole bunch of zeros, then a 5. And you're saying to yourself, oh, that looks like it's getting super close. And maybe I thought, hey, I'm going to do it with more zeros. So I'll just put another couple zeros in there. And it looks to me like it's getting closer to a half. So we know that the limit is a half. And the question really is, why is it a half? Okay, so just in this special case, if it's a rational function, really what you can do is you can compare the two leading terms. So not every place, but when n is really, really big, n squared dwarfs 2n. And so the only term that's going to sort of count are the leading terms, only when n is really, really big. So we essentially know that this function behaves like n squared over 2n squared. But you can reduce that. The n's reduce out, and you get 1/2. And so the output of the function is never exactly 1/2, but the bigger and bigger and bigger you put in the value of n, the closer and closer you'll get to 0.5. And so that's really why mathematicians invented limits. Okay, now let's look at the next one. Okay, so you're like, oh, okay, I'm looking at a limit, things you want to check. I'm looking at a limit, yep. I'm looking at the end behavior because the input's going to infinity. And this is a rational function, okay? So the key thing is, if this is a rational function, when the n's are really big, the output behaves like the ratio of the leading terms, which is n squared over 5n squared, which is, 5n cubed, which is 1 over 5n. Okay, and let's think about this. When you have 1 over 5 times something that's infinitely big, That's like 1 over a giant number.
I'm just calling to see how cute my little dinner looks.
That's my mom. I dropped off dinner for her today.
I'm going to start cooking it, but I just want to let you know.
Okay.
Oh, I found another program on Netflix I thought was good called Virgin River. I started watching it, and I like the characters.
I'm going to let you listen to my mom.
Just thought you might like it too.
She's cute, isn't she?
I love you.
Aw, she's cute. I'll call her back. Okay, so here's another thing you want to know. If you have a fixed number, if you take 1 divided by a giant number, are you guys good that that's going to be about 0? And so this is about 0. Now, the other thing you can work on is we can think about if we have exponential functions, okay? And the key for an exponential function is you can look at the base. And again, we're looking at just the end behavior, okay? So we really got a couple different cases. We can have, let's call this the ratio. If the ratio is bigger than 1, what happens when you power it, okay? R to the infinity, what's going to happen to that? That's going to get huge, right? Okay. If R is between 1 and -1, and you take that R to the infinity, what's going to happen? That radius, that ratio is going to be about 0. Okay, and then the other case is, what if the R is less than -1? What's going to happen is you're going to have these flip-floppings. You're going to get a really big positive number, then you're going to get a really small negative number, and then you get a bigger positive number and a smaller negative number. And so when you have this one, this won't have a limit. And so, do you guys remember Lindsay Lohan? We say that the limit does not exist. Okay, so the key then is to look at the ratio and see what's happening. Okay, so this ratio is between -1 and 1, so this is going to go to 0. The same thing here. And this ratio is bigger than 1, so this is going to get infinitely big. So this is going to plus infinity. And we're timing it by a 5, so that's even be just even bigger. So we know this is going to plus infinity.